Welcome to the IGEL on AWS session, where today I'll show you how to accelerate adoption of your thin client strategy within your organization. I'm Steve Mueller, CTO of Hypersive and former lead end user compute specialist at AWS. Traditional IGEL management infrastructure lives on-premise, but did you know you can put the entire stack in AWS? We'll show you how to go AWS first with IGEL, and why we think virtualizing the thin clients themselves and accessing them remotely is an important strategy for user acceptance and migration. This session is going to move fast. If you miss a concept or feel like this stretches your expertise a bit too much, don't worry. We built this presentation with that in mind and broke the material down into concepts that are easily digested and learned with repeated viewings. And if all else fails, reach out to me directly. The IGEL stack breaks down into 4 major areas: tools to help provision your thin clients at scale, a management plane to configure and scope the runtime parameters and operation of your thin client fleet, a set of administrative services wrapped in a console to interact with the management plane, and the actual thin client endpoints themselves for your customer base to use. Traditionally, IGEL deployments are done on-premise. The core of this stack is straightforward. ICG and UMS servers are installed on bare metal hosts or in virtual machines, the endpoints themselves provisioned on physical client devices, and the UMS console deployed to desktops or laptops. Deployment appliances and load balancers are more fringe scenario and vary from customer to customer. But what does this stack look like when you put it on AWS? The ICG and UMS servers map to EC2 instances running in your VPC. The UMS console is a perfect fit for streaming with Amazon AppStream, and elastic load balancers make excellent front ends for your ICG instances. Outside of this, the deployment appliance and thin clients themselves can also run in EC2 under more conditioned circumstances. So let's break that down. Moving ICG and UMS on-premise workloads to AWS is conceptually straightforward and achievable in practice, so we should expect we'll have that covered. But interestingly enough, moving the UMS console into AWS is also relatively effortless. In fact, did you know you can run Windows-based client applications in AWS and stream them to your local client hardware? We'll show you why and how. And for ICG registration and UMS management of thin clients, elastic load balancers within AWS give you the ability to pick and choose how you want to offer your management services, publicly, privately, or both, with none of the operational difficulty associated with traditional load balancers. Breaking down the ICG and UMS workloads in AWS even further, we see there are 3 core services in use: Amazon VPC for networking, Amazon EC2 for compute, and Amazon Elastic Load Balancing for distribution. With VPC, you build your own private network in AWS, where you deploy and run your ICG and UMS servers. Both run in their own virtual machines or instances within EC2, and ICG instances receive thin client traffic from the Elastic Load Balancing service, which can be deployed publicly, privately, or both. As mentioned previously, you can install the UMS console in AWS and use the Amazon AppStream service to stream the application to your local client device. By running the console remotely in AWS, you can place it in the same VPC with your ICG and UMS EC2 instances, more easily control the upgrade path of the console and therefore its UMS parent, and onboard administrators quickly across the client hardware devices you want. Revisiting our stack diagram from earlier and merging in the AWS services, we now have a visual roadmap for how to get the core IGEL stack onto AWS. There are some initial things to consider, however. When running ICG and UMS on EC2, remember that both workloads run on Linux, but only UMS can be installed on Windows. Additionally, although not technically supported by IGEL today, both management servers do run on Amazon Linux. UMS requires a database, and while you can use the internal Apache Derby database, you can also externalize this to the Amazon Relational Database, or RDS, service. A word of advice here, though. Specifically evaluate your needs for the database. There are perfectly valid scenarios where the internal database makes sense, and others that require the larger capabilities of RDS. For Amazon AppStream, it is a Windows-only service, so you will be installing the UMS console into and streaming from a Windows desktop environment. When looking at your load balancing needs, you can use the domain name provided by the Elastic Load Balancer, or you can define your own in either Amazon Route 53, the AWS service responsible for DNS, or on your own DNS systems. You can also provision an SSL certificate for the load balancer using AWS Certificate Manager, or import your own to support the HTTPS and encrypted WebSocket traffic between the thin client and the backend ICG workload. And as mentioned earlier, you can provision your load balancer as a public endpoint to support thin clients from any network, privately for internal or corporate networks, or both to support scenarios where users work in a corporate office but also work from home with IGEL thin clients. Layering these additional considerations onto our visual roadmap, we now have a more refined vision of how IGEL fits into AWS. Let's take it up a notch now and look at provisioning actual thin clients in AWS. Sure, but why? One of the most common complaints I've personally fielded over the years from customers who own endpoint deployments is a sense of frustration with user adoption. An administrator might spend months planning, developing, and implementing an endpoint strategy, only to have the rollout be significantly impacted by users unwilling to part with their favorite laptop or desktop. When those users voice their concerns to management, or more specifically, fiercely escalate and vehemently oppose the transition, it only creates more stress for administrators, who now have to mollify executive concerns. By virtualizing IGEL thin clients, you can run them in AWS for users to remotely work in and accept as if it was their real desktop. If there's an issue, your users simply disconnect and return to their favorite hardware until you can address their concerns. So go ahead and lower the barrier to adoption, improve the user experience, and build an acceptance plan around remote thin clients. We'll show you how. The IGEL OS doesn't run natively on EC2. You can't provision an EC2 instance with the IGEL operating system, and you can't import an on-premise IGEL machine into EC2. But you can run a hypervisor on an EC2 instance using the bare metal instance types that support the Intel VTX instruction set, and run your thin clients as VMs within that environment, including the Deployment Appliance. So what does that look like? This. If we provision a bare metal EC2 instance, we can run a traditional hypervisor on that instance and create an on-prem equivalent environment for IGEL to run in virtually. And for those wondering, why do this in AWS and not just with traditional on-premise hypervisors? The answer is simple: compute scale and elasticity. Remember, EC2 removes a lot of undifferentiated heavy lifting associated with traditional hardware compute. You can trivially spin up a bare metal EC2 instance with 768 gigs of memory in minutes. You can't do the same with hardware. Once you've provisioned IGEL thin client VMs on hypervisors in EC2, your users can access them using standard VNC clients, using the native remote capabilities that modern hypervisors provide, in full screen mode no less. If your user has an issue on the thin client, have them disconnect and fall back to their local desktop until you resolve the issue. By implementing a connect, test, disconnect strategy, you'll remove a lot of the friction traditionally associated with thin client adoption when it comes time for the real hardware cutover. And in the process, you'll shave months off your deployment schedule. So what does it all look like in the end? This is your playbook for running the IGEL stack, all of it, on AWS. All right, I'm tired of slides. Let's actually show you a demo of this in action. Before we dive into the heart of this demo, we should first keep our earlier slides honest and verify our ICG and UMS servers running on Linux-based EC2 instances. We'll look at the load balancing element and its dependencies. Remember, the load balancer in this demo serves as the public endpoint for the ICG, meaning our instances of IGEL OS can register with it over the public internet. Looking at EC2 in the AWS console, we have two instances provisioned in the Northern Virginia region, one for the ICG and one for the UMS. For the purpose of keeping this demo simple, we have only provisioned one instance of the ICG. The ICG and UMS both support Linux operating systems, Ubuntu, Red Hat, and SUSE being the primary ones. While these distributions are available for use in EC2, we chose to provision Amazon Linux-based instances for this demo, largely to prove the point that, while technically not supported by IGEL, they do work, since there is a population that will be interested in this. Before we move forward, make a quick note of the ICG and UMS IP addresses. Both EC2 instances are provisioned within private subnets of the VPC and get private addresses from the address block defined by the VPC, which in this case is 10.101/20. Switching gears now, let's take a look at the load balancer and its related dependencies. In our demo, the load balancer will listen for both HTTPS and WebSocket traffic on TCP 443 in the public endpoint space, and forward to the ICG instance on TCP 8443. That means we'll need to provision an SSL certificate for the load balancer. We can do this using Amazon Certificate Manager, or ACM. The load balancer itself is comprised of two parts, the target group and the listener. The target group seen here defines the ICG instance listening on TCP 8443. We see that the load balancer is an application load balancer, or ALB for short, configured to listen on TCP 443 for HTTPS traffic. It uses the public certificate we created in ACM and sends its requests to the target group from the previous screen. It is important to note that the ALB supports both HTTPS and encrypted WebSocket traffic, which is critical for the ICG and UMS communication. Although not visible here, we recommend you set the ALB session timeout to the backend ICG target group to 3600 seconds or 1 hour so that WebSocket traffic stays connected. While the load balancer provides a DNS name, we want to use our own for this demo. We've defined our DNS name, disrupt.alpha.aws.hypersive.com, in Route 53 as a CNAME record. Just to show you that all of this is really in AWS and that there's nothing up our sleeves, let's do an NS lookup on the CNAME record. We'll pull up a command prompt, run NS lookup, and enter our CNAME value. As you can see, the record is a match, meaning we are in fact publicly hosting this record, and it resolves to the load balancer. Now that we've verified all of our ICG and UMS infrastructure, let's verify our AppStream installation of the UMS console. We'll do this by first logging into an AppStream session. Once we've provided credentials, we'll wait for the apps to load that have been dynamically assigned to us. A quick shout out to Liquidware here as well. We're huge fans of using their Profile Unity product for dynamic app publishing within AppStream. Once our apps are loaded, we'll launch the UMS console and wait for the login prompt. One thing we should observe: the UMS IP address from earlier is the same one being used here, meaning this is our UMS instance in EC2. Now that we're in the console, we see that our ICG self-signed certificate is set up, as is the mass deployment key that we'll use for ICG registration. Note the load balancer DNS name is also provided on the cert. We also see that our ICG instance in EC2 is fully connected and paired to the UMS instance. This means that everything is running correctly in AWS, and it's time to move on. Now it's time to focus on getting our IGEL OS thin clients up and running in EC2. For the demo, we'll be using VMware Workstation to keep it simple, but most customers will want to use VMware ESXi or Microsoft Hyper-V, both of which will work here as well. For the hypervisor, we're using an M5 Metal Windows EC2 instance. To provision IGEL OS thin clients at scale, either virtually or physically, you'll want to use the Deployment Appliance. It's a small Linux-based appliance from IGEL that will provide a PXE boot network environment for your thin clients to boot against during their initial start, and will deliver the OS firmware you specify in its web interface. There are two virtual networks here. One is for the air-gapped PXE boot network, where the Deployment Appliance lives and the thin clients boot from, and the other is for the NATed VM network, where the thin clients will eventually run. Okay, now for the interesting part. Let's provision an IGEL OS thin client as a VM. In our demo, we'll use a VM template that we've predefined in OVA format as our starting point. In VMware Workstation, we'll have to open the file directly, but in ESXi or Hyper-V, this template would almost certainly already be located on the data store. Note that the VM template does not have an operating system installed. Since we're installing IGEL OS over PXE, the VM itself does not have an operating system installed. We need to make sure the VM starts on the PXE boot network so it can install OS firmware from the Deployment Appliance. IGEL OS doesn't need much hardware to run, and local hard drives are limited in size by the operating system. We've assigned a lightweight hardware profile to our VM here. Okay, Time to get the OS installed. Let's power up the VM and let it pixie boot from the network. When you see the Grub bootloader menu appear, you know you're talking correctly with the Deployment Appliance. At this point, the VM downloads the OS firmware media from the Deployment Appliance and prepares it for installation. Of course, you don't need to touch anything, so grab a coffee or check your email. Back from your coffee yet? No hurry. The OS is now installing. Again, you don't need to touch a thing here. When the installation is done, you will need to change the network to use the VM network, so the post-install ICG registration can be completed. You can do it now or when you're in the OS interface. Now that we're on the desktop, you'll need to step in and finish the post-installation configuration. Unfortunately, there's no easy way to automate this just yet. Okay, it's go time. Let's register the OS with our ICG instance in EC2, using the public load balancer DNS name. Note that we have to specify the port here, not just the protocol. We'll punch in the mass deployment key shown earlier in the UMS console, and our OS will finish registration before rebooting. While the OS boots to its first usable state, think of everything we did to get here, and how much faster this is compared to a traditional on-prem or physical environment. Now for the moment of truth. We are successfully registered with the UMS and taking profile deployments. We should verify, however, that we are in fact registered. Let's grab the hostname and confirm this in the UMS console. Jumping back into the console, we'll navigate to the UMS Administration tab, refresh to get an updated devices list, and expand the devices folder. And there we are. Good news, we're almost done. To finish, we need to enable VNC access into the VM for our users. We'll do this by utilizing the VNC feature implemented by VMware and Microsoft hypervisors. Configuring VNC is a manual step for VMware Workstation, so consider automating this for more advanced hypervisors. Users will access their VMs by pointing their VNC clients to the EC2 instance for the hypervisor, and providing the port that was specifically used for their VM. On one final note, there may be a better way to remotely access IGEL instances at scale. To get into our IGEL OS Thin Client VM, we'll need a route into the VPC, which is achieved over one of three transports: client-side VPN, site-to-site VPN, or AWS Direct Connect. Enterprises already using AWS will almost undoubtedly already have this in place for their corporate to AWS integrations, using site-to-site VPN, Direct Connect, or both. For our demo, my corporate network is already integrated with AWS, so I'll simply VPN into my corporate network from my Microsoft Surface laptop using OpenVPN client software. This will give me the route I need into AWS. Time to fire up the VNC client and access the VM at 10.101.8.17:5901. And we're in. As you can see, we've connected to the remote IGEL OS Thin client, and we can verify that it is in fact the one that we provisioned. It's important to note that we're operating in full screen mode at 1920 by 1080 resolution. I've completely forgotten there's a Windows desktop behind me, and I'm totally immersed in the IGEL OS experience. This is my reality now. When I'm done with my session, or I need to return to my local Windows desktop environment, I simply disconnect the VNC client. This makes user acceptance testing easy to implement and far less painful than if real hardware was used. Simply connect, test, and disconnect without changing a thing. We've covered a lot of ground today in a very short time. I'm sure there are questions, so fire away, or contact me directly offline. Thanks for attending.